Okay, so it's probably appropriate for me to mention just, very first thing, I am recording. I record all my lectures. I have for from many years pre-COVID, by the way. I was an early adopter. I think it's just appropriate to let everybody know. So it is recording. So hypothetically, if you say something, it could conceivably be picked up by the microphone. It's pretty sensitive to distance, so you're probably fine. But anyway, FYI, for legal purposes, you've been informed. Okay, so I hope y'all all got the email that I sent on Friday and have had a chance to watch the video where I went through this outline of, again, various bits of advice and organizational details and stuff like that. So if you haven't already, do make sure to watch that video. It's very important, a lot of details that are important to the course. Blah, blah, blah. And let's see here now, if I can, let's see here. So on to course material. I like to start with this question, why are we here? Roughly speaking, why are we taking a course in multivariable calculus? Now, I know that for many of you, the answer might be because my major requires it. That's fine. So, related question, why does your major require you to take multivariable calculus, right? Okay, so this is a really important question to have a good understanding of. And I'm going to start by kind of taking off from something I think you already believe, which is hopefully you're already persuaded that single variable calculus is important. Most single variable calculus classes include tons and tons of examples of applications of, hey, look at this problem that you can solve with calculus and look at that problem. And most single variable calculus courses will do this for a variety of different fields. They'll have econ examples and biology examples and physics examples, et cetera, et cetera. So I hope that that you're willing to take this as a taking off point. So in particular, derivatives. What's so great about derivatives? Well, they help us describe how things change. So if you're ever in a circumstance where you're keeping track of something that's changing, all right, of course, well, that's a pretty big tent, isn't it? Things that change. Lots of things change. This one's a little bit harder to phrase. Why do we care about integrals? I like this idea of what I call an accumulating quantity. And we're going to talk a lot about accumulating quantities in this class. To me, this is, just to say it simply, anything where the whole is the sum of the parts. Right? And that's, again, lots and lots of different things have this feature. Not everything, but lots and lots of things have this feature. And integrals are an approach to computing such things. Okay, so again, single variable calculus. Hopefully you're already persuaded. So, okay, here's the problem with single variable calculus. And let me go ahead and switch over to the full screen mode here. The world is three-dimensional. It's not one-dimensional. We did seem to solve a bunch of single variable calculus problems that helped us understand our three-dimensional world, but in very many of those cases, there were some big, unrealistic assumptions being made, right? And so let me just show you a couple of ways in which things can get uglier that single variable calculus can't really handle. Right? That are nevertheless about kind of, if you will, sort of derivatives and integrals, things changing and accumulating quantities. So here's a real simple scenario right here. Let's suppose in this room, for example, temperature, not a constant. Right? It's probably warmer by the window in this next to where the sun's coming in, and it's cooler in this nice dark corner down here. So temperature could be thought of as a function of position. Right, so you give me a position here, we can talk about what the temperature is. You give me a position over here, talk about the temperature over there. Right, so a multivariable function. If I am currently here and moving with a certain velocity, how fast is temperature changing? And you might just think, oh, you want to know rate of change, you take a derivative. Yeah, okay, but derivative with respect to what? Temperature is a function of three different variables. which variable? Maybe kind of all of them in some sense, but like how do we deal with that, right? Hey, come on in. This is one of the questions that we're going to answer with multivariable calculus. And you can see that this is the kind of thing where, single variable calculus kind of addressed questions sort of like this, but it crashes and burns on a highly plausible, I did not have to go into some weird niche, abstruse kind of area to find a problem where single variable calculus is going to kind of choke, right? So multivariable calculus is necessary to answer simple extensions like this of ideas you've seen in single variable. Whoa, I hit the wrong button. Sorry. Okay, now I'm lost. Where am I? Okay, here we go. Okay, next, let's look at this example right here. Y'all have seen examples, I assume, where you want to compute the amount of mass of a certain lump of whatever, and they give you density, right? Mass per unit volume, right? But they tell you density is a function of what variable? Now, sometimes this happens, right? So my favorite example is if you have a tank full of sludge. The sludginess of the sludge tends to settle to the bottom, and the less sludgy tends to rise to the top. And so density might realistically be a function of just one variable, height. Sure, absolutely. But it isn't always. You can go into the woods out there and pick up a rock, right? The density is not constant, and it depends on more than just one variable. All right, so how do we answer questions like this? How do we add up all these little bitty pieces of mass? I've got this lump here, and I can think of this as little pieces of mass, but how do I add them all up? If I were to take a slice, like you imagine in a single variable calculus context, the density is not constant on that slice. What am I supposed to do with a density function on a slice of volume? If it's not constant, you can't do anything with that. How do you get around this? Multivariable calculus is going to totally answer this question for us. Right? And again, you can see I didn't have to go into some, distant, narrow, abstract kind of application to find something that single variable calculus chokes on. Right? This is rocks out in the woods, pretty relatable, right? So big gaps in what single variable calculus is capable of, and multivariable calculus will fix those gaps. Okay. So now that those were just the low-hanging fruit, right? And to address the concern that maybe, who really cares about rocks, right? I don't really care about the temperature in the room, whatever. Right? So I like to show you some examples from specific fields of study. Now, this first one here anyway, this is not a real economics equation, right? I just kind of wrote down some stuff. But that said, economic models very often kind of have this general structure, namely there's a bunch of different variables that are related by way of an equation, in which none of the variables has been solved for. And in this case, it'd be pretty hard to solve for most of those variables. Right? So take P in particular. If I were to try to solve for P here, the problem is P is it's inside of an exponential, and it's also outside of an exponential, and these are not tractable. You can't solve for P realistically. So, reasonable question then. Suppose I'm interested in how fast P is changing. And why is P changing? Well, P is changing because the other variables are changing, but because of the equation, P has to change to adapt to how the other variables are changing. And suppose I know how fast the other variables are changing. Right? So if I know all of these, and I want to know what that is, how do we do that? Right, how am I gonna solve for the rate of change of P if I can't even solve for P? Right? So this is a very, very common problem to have to deal with in economics. And how do you do that? Well, multivariable calculus is going to be the answer. There's an idea called implicit differentiation and the implicit function theorem that addresses this question. So this is one of the things that we're going to be able to deal with thanks to studying multivariable. By the way, I also like this example for another purpose. There is a common misconception, I think, out there, that we live in a three-dimensional world and therefore 3 dimensions is enough and we never have any possible need for more than 3 dimensions. I mean, four dimensions, how would we ever have 4 dimensions? Can't even imagine. Is this like a sci-fi movie or something? Who needs 4 dimensions unless you're going to study, cosmology or something like that? Okay, that's a bunch of nonsense. Absolute nonsense. And this example shows it. Right? We have here 5, arguably 6. It's what we call 5 plus 1 variables. Because there's time is the plus 1. So we have, again, depending on how you want to count, 5, maybe 6 different variables here. So we could view this as being a math question in 5 dimensions. Well, now, again, from a geometric standpoint, you can't possibly visualize that. Don't try, right? Your brain will melt. You can't do it. It's not realistic. Nevertheless, economics is a thing, right? It is not at all weird to have, various economic variables, price, quantity, interest, capital, labor. These are run-of-the-mill, everyday economic quantities that might very well be related in certain situations in certain ways. Right? So doing math in more than 3 dimensions is utterly routine. Right? And so don't fall for this line that anything above 3 variables is abstruse. It's really not. Okay, moving along. Now there's some scary looking equations. These are called Maxwell's equations, and they're big players in E&M. By the way, some of y'all are engineering majors. By the way, just curiosity, show of hands, engineers. Any physics majors, possibly? Any chemistry majors? No? Okay, so a lot of engineering and physics anyway. And so y'all are going to see these equations quite a bit if you haven't already. What's going on there? Right? Well, there's a bunch of things going on here. For one thing, we're going to have to talk about what that means right there. And that's one of the things we'll do in this course. It's essential for being able to understand these equations, to understand what do the various symbols mean. So like, what is that? Here's a weird looking one. That would appear to be a differential, but it also appears to be a vector. What's going on there? Right? And et cetera, et cetera. So a bunch of symbols, we're going to have to figure out what they mean. But then, in addition to, what do the various symbols mean, another really good question is, what's the best way to think about this statement? And we've got various mathematical objects we're going to have defined. Y'all can believe me when I tell you that certain relationships hold between them. But why is that true? How should you think about that? What point of view can you have in your head that will take you from I'm willing to believe this is true to I totally get that this is true? I don't have to believe you. I get it. You should believe me. That kind of thing, right? So that's going to be one of the things we're going to aim for. And of course, y'all heard me talk on the recording about how this is a course about ideas, right? It is not a course about, memorize and regurgitate, et cetera, plug and chug. That's not what we do here, right? So how to think about stuff like this is going to be a big item for us. And then related note, okay, so we understand all these objects. We understand how to think about the equation. Next question, how does that help me understand electric fields? right? And that's, if you're an engineer or a physicist, that might be arguably what you're ultimately the most interested in, right? And I have to me anyway, very satisfying answers to some of those kinds of questions that we'll be talking about as well. Okay, all right. We don't have any chemistry majors. At least I didn't see any hands for chemistry. But another big thing in physics, and those of you who are engineers will kind of need to know at least a vague little bit about quantum mechanics, right? And one of the big equations of quantum mechanics is Schrodinger's equation, one version of which is this. So again, standard, what does this mean? What are these various symbols? How do you solve this? We're not going to talk about how to solve Schrodinger's equation. This is a partial differential equation. It's not what this course is. But we will talk about the objects in this equation. And in particular, this right here is a big deal. We're going to study this quite a bit. Okay. All right. So, again, my goal with these three examples here is to try to persuade that multivariable calculus is not just, a minor sort of supplement to single variable calculus, right? There are big questions, field specific, like in econ and engineering and physics and chemistry, depending on, blah, blah, where multivariable calculus is critical. I mean, you just got to know it. If you don't know multivariable calculus, you can't do it, right? It's a non-starter. So, why is multivariable calculus important? Why are we here? Why are you taking this class? That's why. Does that make sense to everybody? Everybody on board? Okay. Cool. Okay, so real quick before I move on to the next thing. You know what? Let me just hit this last line. I think this is a really nice little pithy summary. I like to think of multi as being the calculus of the real world. Rolls off the tongue very nicely, nice and pithy. And again, the real world is multidimensional, right? There are multiple variables to be dealt with in lots of situations, and so I think this is a reasonable statement. So. Okay, yeah, so before I go on, some of y'all came in after I had started. No big deal, but today I have to do an attendance check so that the registrar basically can make sure that the correct students are enrolled. So if you came in after I was checking names and if I didn't get you checked off, if you could hang out after class for a second, just make sure I get you marked present. This isn't part of the grade thing, but this will prevent you from getting a frantic email from the registrar summer session or something like that, wondering, hey, what are you doing? Okay. All right. On to book content. So starting with section 1.1. Let me start by addressing this little comment right here. This class, you heard me say during the organizational recording that there's a ton of material in this class. Just a ridiculous amount of material. And how do we get it all done? The answer is you will get it all done, and I will be along with you for much of it. So it's just no other way, right? I've tried for years to get it all done, and what unavoidably happens is that I spend too much time on things that are not that challenging, that y'all can read, maybe come up with some questions, ask in office hours, and be in good shape. Right? And then in exchange for spending time on that in class, I then am very short on time later in the class when the material is getting legitimately challenging, where we really do need to talk about a lot of things. The kind of stuff that you can't just kind of read and figure out for yourselves, right? Stuff where I can really help, right? And I don't think it's an efficient use of time for me to, walk you through things that, again, with the combination of the notes and the book and maybe asking a few questions, you can just kind of handle it on your own, right? It's just not a good use of class time. So y'all will see this in my notes in various places, more at the beginning of the course, less at the end, but sprinkled throughout. And when you see this, that's a cue for you that this is needs to be on your to-do list, right? This does not mean that you can ignore it, right? This, quite the contrary, means that this is something that you have to be your primary resource on reading and learning that material. So whatever system you want to have for this, if you want to circle it in red when you see this, whatever. But don't just let it slide. Now that said, very often I will say a couple words about the stuff that I am going to not cover in class. So, for example, here, y'all can read this. This is a comment about notation. Y'all don't need me to talk about that. But I do like to make the observation here that when you look at these two different notational options for representing that vector, I like to emphasize that this one, you can see the algebra in it. Now, whatever, it's just notation, I suppose, right? But algebra is a good thing. I like to see good things so that I know, so that I have a visual reminder, hey, I've got an opportunity here. Algebra's on the table. I like to use algebra. So anyway, I prefer that notation for that reason. And I also want to point out, make sure you're very clear in your mind about this natural correspondence between points and vectors. I would imagine this should have been covered in your linear algebra prereq class that you took. But if you're not entirely clear on this natural correspondence between points and vectors, that'd be a fabulous question for office hours. Right? By the way, reminder, my office hours are basically right after class. I think I listed it as 12:30 to 1. Because sometimes right after class I need a minute, to go to the bathroom or whatever. But very usually right after class I will go down to my office and we'll start right away. So in effect, it's almost like 12:15 to 1, kind of, sort of. So anyway, if you can stick around for a couple minutes after class, if you are not clear on this natural correspondence, perfect question for office hours. Okay. All right. And then there's a notation question down here. Very often we find ourselves referring to points X, Y, Z in space. And I'm going to use the sort of standard physics convention to call this the R vector. That said, in previous years, for a long time I used this notation. I called it the X vector. So if you look back to my old exams, or if you watch some of my recordings from previous semesters, you might see this notation X. And again, it's just it's just notation. It's just how I was referring to X comma Y comma Z. Okay. All right. Okay. Moving along. Oh, by the way, let's go ahead and note for the record, that's all I will be saying about section 1.1. Now again, tough choices. That doesn't mean this is all you have to know about 1.1. I have to make these tough choices of how to spend class time. Class time is very valuable. We only get so much of it. There's an unbelievable amount of material to cover. I will straight up skip quite a bit of stuff, right? So that is, again, just because of the tough choices aspect of things. It's not that you don't need to know it. So you are responsible for everything on the content syllabus. So make sure to read section 1.1 carefully. Okay. All right. Moving along. So there's, again, a bunch of stuff in 1.2 that I think is very readable. So make sure to read all that, of course. I do want to spend some time talking about parameterizations. I think this is probably a new idea for most of you. And it's an important idea, something we're going to do a ton of stuff with. So here's the big idea. Parameterization is just position as a function of a single parameter. And by the way, very often it's convenient to think of that parameter as being time. So think of a parameterization as position as a function of time. It's a pretty natural construction when you think about it like that. Okay, and also relatable. Position as a function of time. Well, that's what happens when you draw things, right? The tip of your pencil as you draw something at any given point in time, the tip of your pencil will be on the page at a particular position. Does that make sense? Everybody happy with the idea that that drawing is the perfect sort of real life metaphor for what I'm going to call here a parameterization? So here, let's see an example. Whoops. Here's an example. Position, x comma y, compactly denoted as r vector. Position as a function of time. Right? So this is a parameterization, and specifically these coordinate functions are cosine t and sine t. Okay, so let's try to understand. I mean, I've got a formula here that says for any given time, here's where I need to be. This is telling me how the tip of my pencil is moving as I'm drawing something. What is it that I'm drawing? And this is a question category of questions that the way you answer. There's different methods that are, different tools for different purposes. Basically, there is no single way to answer this question. And by the way, it's an opportunity for me to introduce a metaphor that I like to use a lot. I think a pretty good way to think about I'm going to show you various different tools for how to, given a parameterization, how to figure out what does this thing look like. And I like to think of each tool as being like a tool in a toolbox. And, in a toolbox you might have a screwdriver and a hammer and a wrench. And hammers are good for certain things. They're not so good for other things, right? And likewise. So think of, a lot of the things I'm going to show you are just tools for your toolbox, right? And they're useful in certain circumstances, not in other circumstances. And by the way, sometimes you have specialty tools, right? I don't know how much y'all know about like tools and stuff, but there are different kinds of screwdrivers that, are useful in different circumstances. They're all about screwing a screw into a piece of wood. But depending on the situation, you might need one kind versus a different kind. And so what we're going to see here are three different kinds of screwdrivers, basically. In all cases, we're going to be looking at trying to find, what is this curve that's described by this parameterization. But the particulars will make different methods useful in different cases. Okay, all right. So for this first one, you just kind of notice, right? So this particular method, the heads up method, you just notice that. Well, look, x and y satisfy pretty hard to forget relationship, right? We have this Pythagorean relationship between sine and cosine. And so I have here an equation. Every point that's produced by this parameterization, every point that the tip of my pencil travels along, satisfies this equation and therefore will be on this circle. Right? So, all right. So again, just by this sort of, head on a swivel method, boom, I know what this is. This is parameterization of a circle. Is everybody on board? Okay. Great way to solve that particular problem. On the other hand, we got lucky. You will not always get lucky. Okay, so here's a different tool for a different kind of problem. Let's look at this parameterization right here. Now, quick reminder, don't forget, when we talk about position, that's x and y, right? So in particular, this thing right here is x, and this thing right here is y. I won't always write out like I did in the previous example. I was very, explicit that, okay, this is X and this is Y. It's kind of bulky to have to write that down every time. And I don't really want to. Most people don't. Right? So anyway, make sure to remember when you're given position as a function of time, literally you know what the variables are that are those given coordinates. Okay, so this method. Another tool for your toolbox. What we do here, solve for t in one of the equations, and then take that formula for t and plug it in to the other equation. In this case, this worked great, right? I mean, it's easy to solve for t in this first equation. If I have x equals t minus 1, solve for t, no big. Plug that into where t is in the second equation. Keep in mind this is y equals 3t plus 4. And out falls an equation. And so, again, our goal here was to figure out, what is this thing? And the answer is, it's a line. Everybody happy? Now again, which method do you like better? Trick question. Don't choose. You need both. There will be those circumstances where this is the move and this will be useless. And there will be those circumstances where this is the move and the get lucky and notice the answer method will be useless. Okay. All right, here's another method. We're going to be looking at this same parameterization here. And again, don't forget, this is x, and this is y. Sometimes, not always, sometimes you will notice a relationship between these formulas, the formula for x and the formula for y. And what you see here, the algebra that I've done, is just sort of a recognition that, look, the formula for x is like, I have a constant times t plus a constant. The formula for y is constant times t plus a constant. Oh my gosh, come on. Structurally, they look a lot alike. And then you just notice it doesn't take much doing. I can take the formula for x and I can manipulate it. I can multiply it by things and add things, whatever, and produce the formula for y. And if you do that, and of course, obviously, you got to do that to both sides of the equation. Right? Notice that what you end up with is, missed. The same equation between x and y that we noticed previously. So again, sometimes this will be the by far most desirable way to proceed, and this will stink, and vice versa. So tools for your toolbox. You need to have various different tools. How are we doing? By the way, let me, another procedural point about class. I do a lot of talking, right? This is a lecture style class. But if you have a question, I'm happy to get questions. So periodically I will try to make a conscious effort of stopping, leaving some dead air, right? And hopefully someone will throw out a question. How y'all doing so far? Is everybody with me? Okay. Mid-lecture, if a question occurs to you, you are also welcome to raise your hand. And if I'm right in the middle of something, I might say, here, give me a second, right? But I will get back to you hopefully very quickly. And that's also totally fine. And of course, y'all seen the web page, and there is a one of the links on the class web page is this blurb that I wrote called "Asking Questions." I think I called it that. And there's a lot of considerations about when you have a question in class. should I ask that question or should I not ask that question? And very often the answer is yeah, absolutely, you should ask that question. And there are some cases in which maybe not. So anyway, I go into great detail about, how to help you make that decision. And so make sure, among many other things that I've given you to read, make sure to read that discussion as well. Okay, moving along. 3 dimensions. Right, here we have position with 3 variables. That means we're in 3 dimensions. Right, so this is X, Y, and Z. Okay, so don't try to find an equation. If there were an equation, the equation would give us a surface. This is clearly a curve because, again, position is a function of time. We're clearly drawing something, right, like that. So it's a curve, not a surface. So none of the above methods are going to work. This is a harder category of problem, frankly. Right? How to figure out what is this parametric curve in space. So again, there are some methods that work in some cases. The following I think is really nice when it works. You're going to notice right off the bat that we've already sort of studied that, right? The whole cosine and sine thing, right? We already know that's a circle, right? Those are the x and y coordinates, and if you think about it, what that's telling me is that's telling me what the x and y coordinates are doing. Let's see if I can switch to the pencil mode here. It's telling me that the x and y coordinates are kind of moving around in a circle. Sort of like that. Now, it doesn't tell me anything about what's happening vertically, right? The x and y coordinates are only telling me about the projection in the xy plane. Okay. So, what about this? Ignore x and y, thinking only about z. If z is t, let's just think this through for a second. As time passes, as t increases, what happens to z? Well, z is also t. So all this is saying is that as time passes, my height increases at a consistent rate. Right? So, what does that tell me about the actual path, the actual curve? Well, I know that the shadow is doing this, right? It's going counterclockwise in the xy plane around the origin. That's what my xy shadow is doing, and I also know that my height is rising at a constant rate. So you can take your sort of geometric intuition, right, all together, you kind of combine them together. What is the curve whose shadow goes around in a circle and that sort of rises at a constant rate? And, well, this is kind of how you would do that. Like that. So you got to use your geometric sort of intuition there. Yeah, great, yeah.
What do you mean that the equation would be a surface?
Yeah, so, this is something we are going to talk about more later on. But I'm going to say generically, when you have an equation of 3 variables, so we're thinking about points in space, in other words, right? And you're just looking at one equation. Generically, that will be a 2-dimensional thing like a surface. Now, why is that the case? Depending on how you look at it, a very deep question, and a lot of anomalous counterexamples, and a very very big discussion. But just sort of generically, you can think about it as if you have this one equation, pretty much for any x and y, you can just kind of fiddle with the z and find what the z is that's going to make the equation work. And so generic, now counterexamples, I'm not saying that'll always work, but not surprising if it would. And if you think about it, if for any x and y there is a corresponding z, we're talking about a surface. Does that kind of make sense? Yeah. I mean, again, it's not perfect, and it's also not always true. but it's most of the time.
So is it possible to describe this helix as a single equation, or?
It is possible, but it's not convenient.
Okay.
Yeah, it's a very unnatural way to describe the helix. Which, by the way, it's a great segue for me because another point I like to make is different ways of describing describing geometric objects with algebra. It's another tools for your toolbox kind of thing. It's good to know how equations work, but sometimes equations stink. Right? If I wanted to describe this with an equation, again, it is not easy. Right? Much easier to describe it with a parameterization. And there are other ways to describe geometric objects, and that's actually going to be a big topic we're going to talk about in Chapter 2. Yeah. So much more to come on that. It's a great question. You happy with the answer?
Yeah, thank you.
Yeah. Anybody else? Okay. Now, all of these examples I've given you, the parameterization was given, and the question was, what's the curve? I want to turn that around backwards now. Suppose I know the curve, and I want to know how do I create a parameterization. By the way, this is a really important thing to know how to do as well. And frankly, I think one of the big shortcomings of many multivariable calculus textbooks, including our own, which I like very much. I think our textbook is actually really very good. But it does have a little bit of a disappointment that they don't spend any time talking about how to create parameterizations. And side note, so I'm a mathematician, but in my college days I did a second major in physics, and so I spent a lot of time solving physics problems. That a lot of y'all are going to spend a lot of time solving physics problems too. And my experience was very often I had to create my own parameterizations. Right. So anyway, I think this is an important subject, and again, you won't find much help on this in the book. But how do you create parameterizations? Here's my number one favorite desert island parameterization method. It's what I call the graph parameterization. You'll see why momentarily. If you're looking at a graph, and by the way, graph, we'll say much more about what a graph is later on. Get real precise about it. But for the moment, it's where you have one of the variables solved for as a function of the others. So very important. To call it a graph, we need to have solved for one of the variables as a function of the others. So if you have a graph, not everything is a graph. But if you are fortunate enough to be looking at a graph, if this is the curve that we know, the method is so easy. Just let t be the input variable and everything will fall into place. It's totally awesome. Look how easy in the following example. This first example, you see we are fortunate enough to have a graph, right? We've solved for y as a function of, well, there's only one other variable, x. Okay, so we're going to let t be the input variable. The input variable is x, so I'm going to let x equal to t. And here's the thing, if x is equal to t, then it kind of follows that y sort of has to be t squared. Because if t is x, and if y is x squared, then, well, y is t squared. And oh my God, we win. We have parameterized because by following this method, let me clean up the mess. By following this method, we have position as a function of time. Everybody happy? This method is so convenient, it almost seems like we didn't do anything. Right? But I think it's very important to explicitly acknowledge the process. And again, here it is. Once you have recognized that you have a graph, let t be the input variable, and it all falls together. Okay, another couple of examples. Quickie, second example. Notice this is not written as a graph. I have not solved for any variable in terms of the other. And it'd be tempting to kind of walk away from this one and say, well, yeah, and I can't solve for y. It's all transcendental and stuff. And so I guess we're out of luck. But remember, you don't have to solve for y. You just have to solve for any variable in terms of the other. And you're right, I can't solve for y, but I can totally solve for x. Right? And so with this, and using our usual rule, so now I have a graph because I've solved for one variable in terms of the others. I'm going to let t be my input variable. In this case, y is my input variable for that graph. And with y being t, x kind of has to be that. Let's just plug it in. And we win. Again, we have position as a function of time. Everybody see how that works? Yeah. Mm-hmm.
How do you know if an equation is transcendental?
Oh yeah, that's a big digression. Basically, if you have a variable that's inside of an exponential and outside of that exponential elsewhere in the equation, I don't want to paint with too broad a brush, but don't expect to be able to solve for that variable. Transcendental is what we call it in certain cases, and we don't need to go down that road. But there are plenty of cases where it's either hard or impossible to solve for one of the variables. Yeah. Is that cool?
Yes. Thanks.
Yeah. Okay, next example. This uses polar coordinates. Now, I'm aware that not all of you have seen polar coordinates. If you have, cool. If you haven't, we will talk more about polar coordinates later. For the moment, let me just establish a very quick little picture. The idea of polar coordinates is that rectangular coordinates are sort of like this, where there's your x and there's your y. You kind of based on that rectangle, and thus the term rectangular coordinates. Polar coordinates says, no, we're going to describe the location by an angle and I'm going to call it a distance, and then back off from it. It's not technically a distance, but what I'm going to say, how far you go in that direction. And if you know by what angle to rotate counterclockwise from the positive part of the x-axis, and if you know how far to then go in that direction, that gets you to a point. So it's another way of describing locations. Is everybody kind of okay? Again, much more details to come. We'll talk about that later. Not hard to persuade yourselves, I hope, that this picture gives these equations right here. That's a nice exercise, by the way. Make sure you're good at trig. Persuade yourself that these are the related equation. And then, how do we do polar graph parameterizations? It's basically the same idea. A polar graph is where I've solved for one of the polar variables in terms of the other. And then again, just kind of plug in, and it just kind of all falls together. So if I take this formula for R, just plug in theta squared, notice now I get position as a function of a single variable. And by the way, if you want to do that other move, if you want to let the input variable be t, if you want to say theta equals t, because that's the input variable, you can do that. And then you'll have arguably the same formula for position as a function of a variable. It's just that now your variable is t instead of theta. And if you like t better, okay, you can call it s or Bob, whatever, it doesn't matter. I feel it's necessary to do that substitution in a case like this because you don't want to have x and y being functions of x. So it's just a little uncomfortable to me for a variable to be both an input variable and an output variable. Little nails on a chalkboard kind of thing. But in this case, because we're in a different coordinate system, that just doesn't arise anyway. So this calling theta t is highly optional in a case like this. Okay, how we doing? Everybody on board? Okay, here's a tricky example. This one's clever. Ultimately, not that big a deal, but very clever, and there are some details. And by the way, just another little bit of advice. It is possible to get intimidated by volume of details. And I think this is a sort of an unforced error. Details stink. I don't like details either. Right? Nobody wants to sit around and slog through details. But it's just annoying. That's all. Right? It's just a little annoying. No big deal. It's nothing to actually be intimidated by. Right? So very often there's a lot of details to be worried about, and just kind of as you're facing a problem, my advice is to just kind of all the details. Yeah, set that to the side. That we'll deal with that when we get to it. Right? Try to see big pictures, and then you deal with the details as they arise. Okay. All right. So what we've got here, this is motivated by something that y'all may have seen. I came up with this because I've seen it out in the real world, which is if it's dusk and, it's not quite, sunset maybe, but still a little bright out, but it's not bright, but you can still see, the sun's not really down yet, and somebody rides by on a bicycle. And the bicycle has a reflector, down at the sort of the end of the wheel, and you see this kind of scallopy pattern. Have y'all all noticed this kind of herky-jerky sort of scallopy pattern that the reflector will make? So that's the curve that we are going to parameterize. Right. So, okay, how are we going to get a foot in the door on that? Well, here's kind of the picture. Yeah, see. The picture is, here's my wheel, and here's my reflector. Got the reflector at the end of the wheel. By the way, when we start, maybe let's say the reflector is down at the bottom, whatever. And then as the wheel moves to the right, that two things happen. On the one hand, the reflector starts to kind of rotate around, but of course the wheel that it's rotating around also is moving to the right, and altogether, that's what makes this kind of scallopy sort of a pattern. Okay, so here's the big sophisticated idea. The location of the reflector, what I'm calling P, follows a weird curve, hard to describe, don't know how to get our hands on that, but the location of the axle is very easy to describe. The axle is just going in a straight line. Right? Does that make sense to everybody? Okay, fine. So what though? A little consolation. I'm not actually interested in the axle, but here's the next observation to make. The spoke, you might call it, that's what they call the little pieces of metal that connect the rim of the wheel to the axle. Thin little pieces of metal called spokes. The spoke is also doing something that's actually pretty easy to describe. The spoke, let's see here. The spoke is just kind of going around in a circle. Now, it's going around in a circle that's moving. Yeah, sure. But as a vector, right? The vector that is literally the displacement between the axle and the reflector is just going around in a circle, and that's not hard to describe either. So the cool observation, I'm going to say kind of a deep observation, is that this reflector might be hard to describe, but it is the sum of two easy things. The axle is easy, the spoke is easy. We just have to find these easy things and add them up, yeah.
Is the distance from the center to the point not just the radius?
The distance from the center of the distance, yeah, absolutely. But we're not interested in the distance. We're interested in the vector, right? Does that make sense? So because this distance is the same as that distance, which is the same as that distance, but the reflector is specifically here, right? And so the direction that spoke is pointed is something else that we're going to also have to account for. Is that satisfying? Okay, yeah. Everybody good? All right. So big idea. Sometimes hard things are sums of easier things. And in fact, the inconvenience is, to try to combine a term, the inconvenience is not an accumulating quantity. The whole inconvenience can be much greater than the sum of the partial inconveniences. Right, so this is a basically otherwise intractable problem that we're writing as the sum of two easy problems. Okay, so one at a time. The axle, pretty easy to describe. And again, there's some details here, but the axle, the y coordinate is constant. Whatever the radius is, we're calling that A, right? So the y coordinate's always the same. The x coordinate, now there is a little tricky bit on understanding the x coordinate. And I should make sure not to get too far ahead of myself. I want t to be represented by, I'm making a color choice here. I want t to be represented by this angle. Might seem like an odd choice to call t this angle. The idea is that t is 0 when you're over here, and then as the wheel rotates, t, which starts at 0, will increase as the wheel rolls. So if I choose t to be that angle, then t is kind of sort of playing the role of time. It kind of sort of, let's not worry about how fast we're moving. If you want to introduce a constant to represent your speed, okay, whatever, but it's not really what we are interested in. Okay, so t is going to be that angle. And that said, here's the foot in the door to help us understand the x-coordinate. This x-coordinate right here, where does that come from? Well, that x-coordinate is the amount of road that has touched rubber. And the clever insight is that the amount of road that has touched rubber equals the amount of rubber that has touched road. This physical appeal, purely physical appeal, right? I mean, doesn't it kind of have to work that way? I mean, for example, imagine that there were gears, right? If there were like little gear teeth on the wheel and gear teeth on the road, which would be more of a rail, I guess, then the number of gear teeth has got to be the same. And so you can see there's a sort of an argument along those lines. Again, physical appeal. That rubber equals road. And why this is convenient is because this amount of rubber is actually really easy to describe. That amount of rubber, let me get rid of all of that stuff. That rubber relates to this angle, whoops, wrong color, by an old high school geometry formula. If you have an arc of a circle, right, the arc length is the radius times the corresponding angle. Yeah? All right, clever little argument. Slick move. Oops, if I can get that to... Whoa, what's going on here? Oh, my pen died. All right, we'll go with my backup pen. Okay. Oh, and you know what? Let me pause for just a moment. I have a little cable I can plug this in to recharge it. Sorry for the delay. There we go. Okay, so we know the formula for the axle. Now let's think about the spoke. And again, there's some little detailed devils here you got to worry about. Keep in mind, we've already discussed this angle here. We're calling T. And now I'll remind you the polar coordinates that we made a reference to previously. The polar coordinate angle is measured like this. That's our theta. And between the two of them, they add up to 3 pi over 2. Right? So as T increases, this theta angle is decreasing. Right? And it starts off with T being 0 and theta being 3 pi over 2. And then as it moves, T increases, theta increases. Eventually T is 3 pi over 2 and theta is 0, etc. So you make that observation, and then it's just a matter of sort of remembering, well, we know from the previous page that position as a function of theta is that, and then you take this formula for theta that we just discussed, plug that into there. Does everybody remember your angle addition formulas? My experience, by the way, has been that the great majority of students that take Math219 have faint memories of there being angle addition formulas in trig, but have long since forgotten them. That's okay. No problem. But we do need you to know those formulas. So do make sure to look up the angle addition formulas just for sine and cosine. You don't need to know it for like cosecant and tangent and stuff like that. But the angle addition formulas for sine and cosine, got to make sure you know those. Those are important. We will be using those significantly. Okay. All right. And so it's kind of all over but the shouting at this point. Remember, big picture. If I can get my thing to cooperate. Here we go. The big picture strategy was that the position that we're looking for was going to be the location of the axle, which we just solved for, plus the spoke vector that we just solved for. Axle plus spoke gives me reflector, and so boom, here's your formula for the reflector. So we've parameterized the motion of the reflector. Everybody okay? There's a lot of details here. And again, try to make sure not to get, intimidated, overwhelmed by details. If you just kind of write it down, take it slowly, carefully, right? Make thoughtful choices about how you set things up, right? So this choice of how I set up my parameter T, a good choice, right? And then follow your nose, and it'll work out. Okay. It's a good method sometimes. And again, tools for your toolbox. Not every question's the same. Okay, here's another one. Suppose you want to parameterize a line. And in particular, suppose what I know about the line, suppose I am given specifically a point on the line and a vector parallel to the line. Now, quick reminder, a lot of people, whoa, I hit the wrong button there. Sorry, I meant to do, okay, here we go. A lot of people like to think of the vector being on the line. That's a mistake. Vectors don't have locations. Remember, vectors are directions and magnitudes. This is another good office hours question. If you If you maybe your linear algebra class didn't spend a lot of time on this particular point, but direction and magnitude is what defines a vector. So they don't really have a location. I can't really say where a vector is. So I think it's a mistake to think of it as being on the line, because on implies a location, which it doesn't have. So, but you'll notice no matter where I think of the vector, being, no matter which arrow I use to represent the vector, they're all parallel. So this is a vector parallel. Okay. All right. Okay, if this is what I know, then I can play a similar game to what we did in the previous example. I can say, all right, well, I'm going to use the given point as sort of my starting point. And then I'm going to say, look, I'm going to add to that multiples of my v vector. Let t be just some, arbitrary scalar multiple. And check it out. If you start at r0 and then you, add multiples of this parallel vector v, notice your result, this resulting point will always be on the line. And so as t increases, yeah, sure, that purple vector gets longer and longer, and so I just move further and further down that line and trace out the line. So it parameterizes the line. Is that cool? Okay, so now this one, by the way, comes up significantly, so you probably want to go ahead and memorize this one. Sort of standard strategy for parameterizing a line. Stuff like this is, it's not that it won't come up, but don't memorize that. That'd be silly. It doesn't come up often enough to want to memorize it. That said, where'd it go? Oh, here it is. Yeah. This one, parameterizing a circle with cosine and sine, comes up a lot. You definitely want to memorize this one too. Okay. All right. Moving along. Okay. Here's another tool for your toolbox. Now you notice this is another students to read kind of thing, so I'm going to leave most of the details for you. Let me just hit the button here. There we go. Make sure to read all these details. The big idea here is that if you have a parameterization of one thing, if you deform that thing, you can just correspondingly tweak the parameterization. So, for example, as we just discussed, this parameterizes the unit circle. And now let's think about this ellipse. The ellipse has this equation, and I hope y'all remember from long ago, probably high school algebra, but the 3 and the 2 just tell you what these sort of, what do they call them? Semi-major, semi-minor radii, or something like that. That tells you these values here for the ellipse. So you can think of it as sort of these, which I don't know, maybe they call these vertices, whatever. But I like to think it also as another way to think about that is that these are telling you how much we're stretching the circle. Right? If you take a circle and kind of stretch it out, it becomes an ellipse. So we are, in fact, to get the ellipse, we are deforming something we already know how to parameterize. We already know how to parameterize the circle. If you're going to stretch it out, if you're just going to stretch by a factor of 3 in the x direction and by a factor of 2 in the y direction, okay, well, here's my circle, and here's me stretching by a factor of 3 in the x direction. I just make those x coordinates 3 times as big, and likewise by 2 in the y direction, and lo and behold, we have ourselves a parameterization of our ellipse. So it's another thing to just kind of, just be on the lookout. How often does this come up? Surprisingly often, I would say. right? Not everything is a deformation of something you already know how to parameterize. This is not a magic wand, right? But it's a good tool for the toolbox. Comes up sometimes, and when it does, it's awful handy. Okay. And then this example here, again, a pretty straight read. I'm going to let y'all pretty much read this. But it is a good idea to be careful not to conflate equations and parameterizations. They are strategically, I'll say structurally different things, right? Both of them are kind of algebra that we write down to describe a curve. Yeah, sure. But in very different ways. And as I have written here, parameterizations generate points. Equations test points. Equations don't produce anything. Right? If you have a point, you can plug into the equation and see if it works. But parameterizations literally produce points. Okay, so they relate to curves in different ways. And with that in mind, question comes up of, here is a parametric curve. Yikes, what a weird one. Oh man, that's going to be hard to understand what that looks like. How would I decide where that intersects this plane here? And we're literally just going to capitalize on the fact that one of these generates points, one of these tests points. We're going to generate, with the parameterization, we're going to generate points on our curve, and then we're going to test by plugging into that equation and see which of those generated points satisfy that equation. And you do the corresponding algebra, and that'll give you a value of t, which you can then use to find the point. Okay, details for y'all. I think that's pretty readable. And again, don't forget, if you have questions about stuff like this, where we kind of go over it real quickly in class, ask me. Right? Happy to help. Office hours is a great time for stuff like that. Okay. Probably the last thing we'll do here, let's see here. Yeah, this will be a good ending point. This point tester idea. If you have a line in R3, if you have a line in R3, we know how to parameterize a line in R3. Just talked about that. We did a two-dimensional example, but this is a three-dimensional equivalent. This is a point generator. You give me a t, out comes points, cranking out points, right? Generating points. What if I want a point tester? What if I want an equation for a line in R3? We're not going to get an equation, but I can still get a point tester. And here's the big idea. And this is just a slick move. The big idea is, if you give me some point and you say, hey, is that point on this line? Is that one of the points that's produced here? Well, then I simply need to know, is there some value of t that I can put in there that'll make the equation work? Yeah, the notation? Yeah, totally. I was totally going to do that. So this notation is a little math shorthand. It's just a shorthand. This says there is, or there exists, and this symbol here means such that or so that. There are certain little expressions that mathematicians use so much, and oh my gosh, do I really have to write out the full way? So having a little shorthand is super convenient. Heads up for those. I'll use these shorthands. It's not going to come up super often in this class, but I need to have the access to these notations. Okay, so I just need to know, is there some value of t that'll make that work? And, well, here's the thing, that t I can solve for in each of the corresponding coordinate equations, right? If you were to take this vector equation and kind of combine it all together and look at the three separate coordinate equations, each one of those will have t in it. Each one you can solve for t. These are the things that you get. And then I just make the simple observation that if there's a value of t that satisfies all three of these equations, let me say that differently. If there's a value of t that is equal to all three of these things, hey, wait a minute. How can there be a single value of t that equals three different things? And the answer is, the only way that's possible is if those three things are equal to each other. And so that's the point tester. And this is called the symmetric equations for the line. It's a real slick move. So whenever you have a line in R3, notice it's two equations. The symmetric equations is another way to describe it. Okay, and that finishes section 1.2 for us. By the way, since we're here, real quick, let me just note on the class schedule that I will momentarily in fact, y'all can watch me do it here, just so you can see what I'm talking about. We have now finished page 8, I guess it is. Is this page 8? Yeah. Okay, so we finished page 8, and so boom, 8. And we finished sections 1.1 and 1.2. And so first homework set is already defined, right? So this homework set number 1, right? Today is Wednesday. Homework set number 1, sections 1.1 and 1.2. And that's due Thursday. Note the time here, 11 p.m. Eastern, right? So always 11 p.m. Eastern on Thursday. Is when so tomorrow. And I talked through in the organizational video sort of the process, how y'all are supposed to schedule your time on getting that assignment done. And reminder, this is it's not all of the exercises in these sections. It's just the exercises that are indicated on the content syllabus. Does that all make sense to everybody? Okay, cool. Let me stop the recording. We'll call it a day. I'll look forward to seeing y'all on